So welcome everybody, good morning. And our co-organizer, Emma Carberry from the University of Sydney, is going to tell us about blowing up bubbles into minimal surfaces. Please, Emma.
Well, I mean, it's traditional for the last speaker to thank the organisers. I mean, Holger's done an amazing amount on the ground. And thank you so much, Vladimir and Alexei, for just wonderful talks. All right, so I'm going to talk about blowing up bubbles, and I mean soap bubbles, torus-shaped soap bubbles, and I'm going to blow them up into minimal surfaces. Now, I should say right from the beginning that although I will talk about integrable systems, I wasn't able to work Nijenhuis geometry into things. And so in a way, as compensation, I really want to explain two main things this talk. So one is what were actually the actual results. So given a sequence of constant mean curvature immersions of tori, all of which have the same constant mean curvature. So you could have the situation where this simply converges to some surface, or some subsequence of this converges to a surface immersion. And then that surface immersion will necessarily have the same constant mean curvature. If you're not in that situation, then we show under some pretty mild conditions that after appropriately blowing up the domain parameter and the image, that you can get a surface immersion in the limit, and then that limiting immersion is actually minimal. So the idea that in the limit, by blowing up, one can pass from a solution of one integrable system to a new integrable system. I mean, that's really the main idea of the talk. And the other thing I want to convey is some reasonably standard things about many different ways that one can view these surface immersions in terms of different kinds of integrable systems data. So I thought going through that in some detail might be useful. So these are each, even though I described them in terms of surface geometry, they're each described by, in each case, the conformal parameter satisfies is a solution of some integrable system. For constant mean curvature, we're talking about sinh-Gordon. For conformal minimal immersions, one naturally has the Liouville equation, but we're going to be in a situation where the Hopf differential is constant. And in that case, one could instead consider KdV, which is of course worth mentioning, because if you can talk integral systems, then KdV is your most standard example. So I will explain why blowing up appropriately, and the vast majority of the work is working out what appropriately means, allows the integrable system that you're talking about to change in the limit. So in order to do this, it's not going to be so useful to actually think differential geometrically in terms of surface immersions, or even to think about the solutions of these integrable systems. It's going to be more useful to use a correspondence that gives either one of these CMC or minimal immersions in terms of a matrix valued polynomial, which has no dependence on the parameter z for your surface, but is just a polynomial in what we call the spectral parameter. Now, this will depend only on the geometry of your immersion at some fixed base point. So you fix the base point and you get it. If you change the base point, you'll get a different matrix. And then we're going to blow up at that base point. And so that's in a way why using this particular correspondence makes blowing up easy, because we transfer our data to the data of the immersion just around some point, and then we blow up at that point. And of course, we blow up the image at the image of that point. All right, so I will spend some time now saying how we get each of these immersions in terms of a matrix polynomial, which we call the potential. So I'll go through this in detail for constant mean curvature. There it's quite an old result. And then part of what we did is extend this to minimal. I can't really believe we're the first people to do that, but we couldn't find it anywhere in the literature. All right, so if we have a conformal immersion from just the complex plane into R3, and omega is the conformal factor for our metric, then we can write down the first and second fundamental forms. And here, instead of using mean and so here we write it somewhat unusually, where we bring in the Hopf differential. So we write down the second fundamental form in terms of the mean curvature, the metric, and the traceless part of the complexified second fundamental form, which we've written here explicitly. And then in terms of the mean curvature and the Hopf differential and the metric, Bonnet's theorem becomes that if you give such functions that satisfy the Gauss-Cardazzi equations, then there is a conformal immersion such that these are the metric, the Hopf differential and the mean curvature, and that immersion is unique up to isometries of the ambient R3. All right, so then what do those, what do those systems look like? If we are looking either locally and we assume that we're not in the neighborhood of an umbilic point, then the Hopf differential is holomorphic, and so we can change coordinate z to make that so that the q is constant. And if we're working on a torus, well, then our global holomorphic quadratic differential has to be constant. So if we just assume, if we're locally, we're just assuming we're not in the surface case. So we are able to make q equal to constant either way. And we normalize our mean curvature, and then we make the elliptic sinh-Gordon equation appear as Gauss's equation. So this explains why after normalizing the mean and the curvature and the Hopf differential, constant mean curvature immersions defined up to ambient isometry are equivalent to real valued solutions to the sinh-Gordon equation. The real valued is important. There will be a real structure throughout this that I won't talk about a great deal, but it is important. Now, it's well known that if you have constant mean curvature immersion, that there is an associated family of constant mean curvature immersions. Now, if we look at what the Gauss-Cardazzi equations look like, the most obvious way to get yourself an associated family would be to scale the Hopf differential by something of unit length, and then that will give you an associated family. I'm being at risk of bringing an extra thing in. So we know that when we have a constant mean curvature surface, that one of the two parallel surfaces that's of distance 1/h from that also has constant mean curvature. And we actually pass to that family of parallel surfaces with the form that we're going to take here. It's absolutely equivalent information, but that just ends up being easier in the blow up. All right, so to write all of this down in terms of something that might give us a matrix polynomial, so we're going to identify the ambient R3 with the Lie algebra SU2 in the standard way. And we can get ourselves an extended frame for this family of CMC immersions. It's actually the parallel surfaces. By requiring the extended frame to be the thing which conjugates our standard basis for R3 back to the basis for the standard frame that you would have for your surface. So the Z and the Z bar derivatives and N, where we have inserted a parameter lambda into here for the associated family. So our extended frame, explicitly we can write out how it means that we insert a parameter lambda into what would be the frame for the original immersion. So if we have, so each of these F lambdas for a fixed lambda, right, it's a map from the complex plane into the Lie group SU2. And then we consider f to the minus 1 df. That's then going to be a useful object, because if you have a one form of this form, then it defines a flat connection, and we can study those connections and get useful things out of them. All right, so we can replace our study of constant mean curvature immersion by looking at extended frames, and the lambda comes in this way, where we have a lambda and a lambda inverse, and there is clearly some symmetry here, which is going to correspond to lambda going to lambda bar inverse. Now, this correspondence isn't one way. We can also reverse it. If we have an extended frame, then we only need to differentiate with respect to the parameter lambda in order to recover our family of constant mean curvature immersions. So that gives us an explicit correspondence between a constant mean curvature immersion of the plane up to ambient isometry and extended frames. So maps from what take as parameter both something in the complex plane or in R2 and something on the unit circle, and give us an SU2 matrix. We normalize them so that they're the identity of some fixed base point, and that's the point at which we're going to blow up. So at this point, we've chosen our base point. All right, we're not done. We need to keep rewriting this information in a number of different ways to get something that's going to be in a decent form for blowing up. Well, so first of all, we can, instead of having this this parameter lambda be on this unit circle, we can allow it to be any non-zero complex number. Now, if you do that, you lose symmetry within F, and so it will no longer be an SU2 matrix. In general, it will be an SL2C matrix, but that's okay. And then there's a relationship between the matrices that we get for lambda and the matrices that we get for lambda bar inverse, which I've written here. So then we can study a family of connections, d plus f to the minus 1 df. And because the connection form is of that form, f to the minus 1 df, then that family of connections is flat. So we can study its holonomy. So now I'm going to assume that we have that our original, our solution to sinh-Gordon really is what is all we need to be doubly periodic. And we're going to look at the holonomy of these connections around something in the fundamental group. Now, because the fundamental group is abelian, when I'm looking at that holonomy, it doesn't actually matter. You know, I can pick a generator. It doesn't. I could also take the other generator, thinking of my torus as coming from a parallelogram. I could take either of those, and the holonomy will have common eigenspaces because the fundamental group of the torus is abelian. So I'm interested in the eigenspaces of the holonomy of our family of flat connections. All right. So from those eigenspaces, it's possible to build a curve, a hyperelliptic curve. So we're going to build a hyperelliptic curve. Oh, I've called it y here, later I've called it nu, doesn't matter. Y squared is equal to lambda times a of lambda, and I just need to specify what that polynomial a of lambda is. It's the only thing I need to actually say. That polynomial, I just need to say where its zeros are and what their order is. Well, I'm going to say that it's got a 0 of order n at lambda naught, precisely if the two eigenlines of our 2 by 2 matrix agree to order n at that point. Now, the theorem here, this looks like a construction. The reason why that's actually called a theorem is that the content is that there are only finitely many roots of this polynomial. So the curve that you get has got finitely many roots, and they don't accumulate at 0 and infinity, because we've only got this family of flat connections for values of the spectral parameter that are in the non-zero complex numbers. So we have to complete the curve over 0 and infinity. It turns out, if you study the asymptotic, so that's adding a single point over 0 and a single point over infinity. And it turns out that the branch points of your hyperelliptic curve, there's not infinitely many of them accumulating near those points. You actually get a finite genus curve. And that's essentially coming down to the fact that one's dealing with an elliptic operator on the compact torus, and that there's a finite dimensional count. All right, so we call this the spectral curve of the immersion. And again, we did fix a base point. And if we do that, then we can look at the line bundle on the spectral curve that's given by the eigenlines of the holonomy. So there might be a question coming up, but hang on, didn't I just use eigenlines of the holonomy to define the curve, and I didn't say anything about the base point? Well, what those eigenlines are depends upon the base point that you choose for your holonomy, but whether or not they coincide doesn't depend, because different ones are just going to differ by conjugation by some invertible matrix. So the spectral curve is well defined independent of base point, but what the eigenlines actually are is not. In fact, they vary linearly with the point. All right, but if we, having fixed a base point, we get ourselves a hyperelliptic curve and a line bundle on that curve. Now, in many ways, that's the data that we'll come back to later, but I promised you a matrix polynomial. And the reason why I promised you that was that that polynomial was going to give us an explicit way of blowing up. Now, it's true that the line bundle here depends on our choice of base point. So you could say, well, can't I blow up the curve and the line bundle? But it's maybe a little more difficult to understand what we mean by blowing up the line bundle. So we're going to express this in terms of a matrix polynomial instead. So first of all, we define what we call the polynomial killing field of the immersion at that base point Z0. So we can do that because we have a curve that is, we have a curve and we have a line bundle on it. Now, if we pick a function on that curve, and the function that I'm going to pick, so here I'm really sorry that I did a typo error, because now I've got this function nu, and because I wrote the spectral curve using the wrong letters before, you're wondering what on earth is nu. So my spectral curve is given by an equation nu squared is some polynomial lambda. I just accidentally wrote y before. So that nu squared is a polynomial lambda. I'm going to pick that function, and I want to create a matrix in lambda, so that the function nu is giving me the eigenvalues of that matrix, and the eigenline bundles are giving me the eigenlines of that matrix. Well, you can do this in general if you've just got a holomorphic function on your curve and you have a line bundle on that curve, then you can associate uniquely to that an n by n matrix, so that the function is exactly giving you the eigenvalues and the line bundle is exactly giving you the eigenlines. In this case, because it's a two-sheeted cover of P1, then the matrix you get is a 2x2 matrix. So that's how I'm going to define the polynomial killing field at the point Z0. And by construction then, the spectral curve is just given by the characteristic polynomial of that matrix. Now, what kinds of things does that matrix satisfy? So this is incidentally the matrix that I'm heading for, right? It's a matrix in lambda that depends on the base point z0. We have some symmetry, so it's going to be some polynomial where these constant matrices lie in the Lie algebra SL2, and we have a symmetry between what's going on. So we before had a lambda goes to lambda bar inverse type symmetry, and here that's exhibited in a relationship between the coefficient k, the coefficient of lambda k, and the coefficient of g minus k plus 1. Now, I realize that it probably seems a little bit annoying. Like, why on earth do you have a polynomial that's starting with -1? Why not just shift it up? And it's basically because that negative term satisfies some really important. I mean, of course, one could shift things around, but that negative term is carrying a lot of important geometric information, and so it's more convenient to keep it this way. So the asymptotics of the holonomy tell us what that lowest term of our polynomial killing field is, and we see in particular the conformal factor, the thing which was the solution to sinh-Gordon, appearing there. All right. Now, we had done all this fixing the base point z0. If we change that base point, well, it just changes. It's just going to conjugate the holonomy, and it's just going to change the eigenlines by multiplication by the frame. And so what that's going to mean in terms of this polynomial killing field is that the value of that polynomial killing field at some other point z1 is given in terms of its value at z0 by conjugation by the frame. Now, the fact that it satisfies an equation of this form means that so it's basically related by big add, means that when we differentiate, we get a relationship with little add. And so that means that the polynomial killing field satisfies the following Lax equation. And we could simply have defined the polynomial killing field as a solution, as a particular solution of this equation. It's a parallel section. It's a section of the SL2, the trivial SL2C bundle that is parallel with respect to our connections. Now, it's not just any solution, however, to this Lax equation. That's actually quite important because there will be many of those. But we are taking this unique one that has got lowest degree. All the others are multiples of this one by some polynomial in lambda. So another way of saying that is it's the one that doesn't have roots. And so that particular solution to the Lax equation is the one that captures all the geometry of the situation. Now, as we've pointed out, though, we don't actually really need the polynomial at all values z, just knowing what it is at z0, and then we can use the Lax pair to solve the Lax equation, to solve from there. So that polynomial in lambda, that's called the potential, and that is the promised matrix polynomial that's depending only on the infinitesimal geometry of your immersion at z0. In fact, if you write down the diagonal terms of that potential, you can explicitly show that they satisfy the linearization of the Gauss equation. So they are exactly giving you infinitesimal variations of your conformal factor. All right, so given the immersion, we got ourselves a conformal factor, a solution to sinh-Gordon. Given that, we got ourselves an extended frame. Given that, we got ourselves you can say a polynomial killing field or a potential. The difference is just whether you take the polynomial killing field was a function of z on the torus. The potential was just taking that value at z0. So we got ourselves a matrix polynomial in the spectral parameter. Now, I wouldn't be explaining all this to you unless this was a correspondence. So the process is actually reversible. If you start out with the right kind of object to be a potential for a CMC immersion, and what that is so it's a matrix polynomial where, again, we're starting with the lowest term being lambda inverse, that has the appropriate symmetry. So the kth coefficient is related to the g minus k plus first coefficient. That crucial coefficient of lambda inverse that carried the information of the metric, so that has a particular form. So basically, so that it's empty except for the top right, and that top right is going to carry the information of the metric. And we also need a genericity assumption that if you start with a matrix of that form, you can get back the extended frame. Now, I won't go through that in a lot of detail because we're not going to use it later, but I will just I will first briefly say, well, of course, if you're I wanted to explain both parts of this correspondence. So beginning with the potential, how do you get yourself the polynomial killing field? Well, I said earlier that you get it by solving this equation, that dxi is the bracket of the connection form with plus the bracket of the connection form with xi is equal to 0. And the matrix polynomial, the potential, is, if you like, the initial value of the xi. It's the value that it takes at z equals z0. Okay, but if you're just given that, in order to solve this equation, you need to know what this equation is. So you need to know what that connection form is. So a crucial part of this is that connection form is actually built from the potential. It's built from the bottom two terms of the potential. You can write it down explicitly. If you write out the potential, so we're just writing out letters for the coefficients of the lambda k's, as u, v, w, and minus u, then the following formula tells you what the relationship is to the connection form. And if you were going in the other direction, so if you'd started with the immersion, solution to sinh-Gordon, extended frame, and then getting yourselves this potential, then this is something that would have been proven along the way. So when you're going backwards, you are solving for the polynomial killing field using a connection form that's actually built from the potential. The more difficult part of going backwards, I won't go into in such detail because it takes a little while to explain and we won't use it later. But it turns out that if you take your potential and you solve explicitly for what the polynomial killing field will look like, so you take exponential, so not the polynomial killing field, you solve certain equation explicitly, take exponential of z minus z0 times this potential, then there's a factorization that you can do that is a loop group analog of the LU decomposition for matrices, and that's called the Iwasawa decomposition. And if you take one of the parts of that Iwasawa decomposition, it actually recovers for you the extended frame, which is a very useful thing. Doing that Iwasawa decomposition explicitly is not so easy, but the fact that we can do it is what's important here. So we have a correspondence between the original constant mean curvature immersed tori that we're interested in, and a matrix polynomial, which we're calling the potential. Now that is well known. That's been around for some years. We wanted to take that as our starting point and then blow up. But then after blowing up, we want to be able to recognize what we get after the blow up. And so we needed to extend this to something similar for minimal immersions. And as I was saying before, I was a little bit surprised that we didn't find this anywhere in the literature. But anyway, we didn't. And so we basically worked through and figured out that everything in this correspondence, there's an exact analog. So if you have a conformal minimal immersion from the complex plane or some open subset of it, you can describe that in terms of a solution to Liouville's equation. So again, by using the Bonnet Theorem to describe the by saying that you just need to look at the Gauss-Cardazzi equations, and then the Cardazzi equation is trivial and the Gauss equation has this form. You can write that in terms of an extended frame. It's worth, the reason I wrote this out explicitly now is it is worth noting that before we had a lambda and a lambda inverse, now there's just a lambda. And there's not going to be some symmetry. So previously we had some real structure that corresponded to involution in the unit circle to lambda goes to lambda bar inverse. Now we don't have that. In fact, the only value of lambda for which we have that this matrix is guaranteed to be what I would call real. So that means that it's an SU2 matrix rather than an SL2C matrix is lambda equals 0. But we can analogously build a polynomial killing field. It may look strange here that I've kind of shifted the shape of this around. So instead of starting from -1 and going up to G, I've done it the other way round, starting from -G and going up to 1. That's a choice. And the reason I've made that choice is it corresponds to blowing up around lambda is 0 rather than blowing up around lambda is infinity, just a little bit easier later. And again, the important one, the one that we will actually mostly use, is that there's again a correspondence to potentials of a certain form. In the reverse construction, one has to use a different splitting. So instead of the LU decomposition, so Iwasawa decomposition, one uses a Birkhoff decomposition. It's essentially because we have a different real structure. But in any case, everything goes through analogously. Oh, sorry, scrolled the wrong way. Okay, so we're going to describe these immersions in terms of matrix polynomials that we're calling potentials. So for constant mean curvature, lambda times the potential was a polynomial in lambda, and for minimal, lambda inverse times the potential was a polynomial in lambda inverse. Now, the spectral curve that I talked about before does come into play. Now, I really went through that for constant mean curvature, but for the minimal case, all I have to do is take the characteristic polynomial of this potential, and that gives me the spectral curve. So we again have that construction, even though we're not claiming that the minimal surfaces that we're dealing with are tori. We didn't have a holonomic to talk about. But again, they're both hyperelliptic curves, and if we want to describe our matrix polynomial, well, we just need to describe its eigenvalues and its eigenlines. And the spectral curve, which is the characteristic polynomial of the potential, describes the eigenvalues of it. And we have an eigenline curve exactly defined by the eigenlines of the potential. So again, for blowing up, it helps to just look a little bit at what this data looks like. So for constant mean curvature, we had a symmetry. So we had that the curve was branched at 0 and at infinity, and the other branch points have a symmetry to them. So if you have a branch point at lambda, then you also have a branch point at lambda bar inverse. So just showing this in the picture here. And there are G such non-zero branch points where G is the genus of the curve. And when we look at these sequences of constant mean curvature immersions, I'm assuming that throughout our sequence, this spectral genus remains constant. It's got a geometric meaning. It's giving you the dimension of the family of through which the torus can be deformed and have the same data. All right, so we're going to label these. So we basically, to describe the spectral curve, we just need to say these points. So if you give lambda 1, lambda 2 up to lambda g, then you have described the spectral curve. And I will explain shortly as well that if you want to describe the line bundle, you also just need to give finitely many points. So, and we will order these so that lambda 1 is the one which is closest to the origin. If one's talking about the minimal case, then there is an analogous construction by taking the characteristic polynomial of the potential, but here there's no symmetry. So we do have branching at 0, and other than that, there's really not much to say. C here is just some constant. It's not important, so I didn't write it down. What about the line bundle? So that describes the eigenvalues of the potential. What about the eigenlines? Well, if we again write the potential out explicitly as uv w minus u, then we can, and if we're given the eigenvalue, which remember we've called nu, or sorry, nu over lambda for the potential itself, then because lambda times the potential had eigenvalue nu, and the potential has eigenvalue nu divided by lambda, then you can explicitly compute out a form for an eigenvector. So you can get that an eigenvector of the form 1 and psi, where psi is written explicitly here. Now, because we've got the 1, this is a section of the eigenline bundle that doesn't vanish anywhere. And hence, if we're looking at its divisor, because we would like to describe our line bundle in terms of a divisor, and we know that you can't, that there'll be a whole family of divisors that describe the same line bundle. They'll differ by divisor of some meromorphic function, but I want to pick this particular one. And the divisor of this, it's only the polar divisor. So it's only the polar divisor of the psi's. Then that is going to be a divisor that describes your eigenline bundle. So it describes the eigenlines of the potential. We call that the spectral divisor. And so I've written that out in coordinates here, where I'm given coordinates. So the first thing is the value of lambda, and the second thing is the value of nu. Now, once you've got lambda, what the nu is not so hard to work out. So it's really just the betas that are the information I have to worry about here. I'd like to order the points in my spectral divisor so that, I'd like to say that beta 1 is the one closest to the origin and beta g is the one furthest away, but we didn't actually say, you have to first make sure you've labeled things so that, I forgot to do the min here. Okay, so let me just assume that I'm labeling things so that it's, if I take the I want to label things so that if I've between the pair beta 1 and beta 1 conjugate inverse, because there will be that symmetry in the spectral divisor, I've picked the one that's closest to the origin. Then, and I'm labeling the 1 up to G so that the 1 is the one where one of those pairs is closest to the origin, and the G is where the smallest of that pair is furthest from the other origin. Then it turns out we get a very useful bound on the spectral divisor in terms of the branch points of the spectral curve. So it sits between the correspondingly labeled branch point and that branch point by inverse. Now, that estimate turns out to be quite useful when one is looking at the blow up. So now, having described all that data that gives us the constant mean curvature immersion, or potentially minimal, which hasn't even come in yet, now I need to actually blow up and see why all this matters in the blow up. So suppose we have some sequence of constant mean curvature tori, and I'm assuming that they all have the same spectral genus and genus of the spectral curve, and that they all have the same mean curvature. And I can scale the conformal the parameter z so that my Hopf differential is also the same for all the elements in that, or the Q in the Hopf differential is the same for all the elements of that sequence. Then remember that we called the branch points of the spectral curve were labeled the lambdas with these subscripts, and that 1 was the one which is closest to the origin. So if the branch points of your spectral curve are all, so if this is one that's closest to the origin, if it's bounded away from 0, then they're all bounded away from 0. So if that's the case, then when you take the limit, you get spectral data that's got exactly the same form, the right form to be the spectral data of a constant mean curvature immersion. So you actually get a, so after passing to a subsequence, you actually get another CMC immersion as your limit. So we're not interested in that case. We're saying, so that's a nice case to study, but we're interested in the case where we don't get some surface in the limit. So we're going to assume that the one closer, the branch point closest to the origin, does actually go to the origin, and in the limit of our sequence as n goes to infinity. We're going to blow up we're going to blow up the coordinate z around the base point, and we're going to blow up the immersions around the limit of that base point. Now, we're going to make all that happen by blowing up the spectral parameter lambda and the potential, the matrix polynomial. Now, it turns out that in order to make all this work, what we need is that that none of the branch points of the spectral curves converge to the blown up parameter being 0. So to make that happen, we are going to blow up the spectral parameter exactly by the size of the branch point which is closest to the origin. So we're going to blow it up by Ln, where Ln is the size of the branch point closest to the origin. And that means that in terms of the blown up spectral parameter, the blown up branch points are all have size at least 1. So they're not just not near 0, they're actually outside the unit, so the unit disk. Then one has to work out, okay, so how do I correspondingly scale the potential, which is a polynomial in this parameter? Well, I would scale it by some factor Sn, and it turns out that the correct scaling factor is the square root of the scaling factor that we use for the spectral parameter. And it turns out that if you want to work through these correspondences that I described to you and work out what that means in terms of scaling the coordinate z and the immersion, that we should scale the coordinate z by the square root of our scaling factor for lambda. and we should scale the immersion by 1 over the square root. Okay, so if we do all of those, then we get what I have been promising you. So suppose we have a sequence of CMC torus immersions, and we're assuming that we're in the case where there is no subsequence of these that converges to a surface immersion. We do need to make 2 further assumptions, the details of which are not so important for the process of the talk. The first one is a condition that guarantees that the limiting eigenline bundle and its dual are non-special, and that's something that we need in order for the line bundle to be the right kind of object to reconstruct an immersion. So that's a generic condition, this is just what that non-speciality condition means here in terms of the blow-ups. And we also need some kind of upper and lower bound on the rate of convergence of the points in the spectral divisor. And here's an assumption which gives us that. Under those 2 quite reasonable assumptions, then there will always be a subsequence of the sequence of constant mean curvature immersions, such that after blowing up, as I've just talked about, that sequence of blown up immersions converges locally uniformly to a conformal minimal surface immersion. And I'm calling that, I've got tildes to mean blow-ups, and the infinity means that I've sent n to infinity. Now, it would be nice to have some kind of information about what that minimal surface immersion looks like, at least what the data that we've been talking about looks like. Now, we can actually explicitly go through and write down, so we had a whole bunch of correspondences that gave us the minimal surface immersion. We had its extended frame. We can write down explicitly what that extended frame looks like in terms of the blown up data. We can write down what the conformal parameter, the conformal factor, so the metric, looks like in terms of the blow up. We can write down what the potential looks like, all of which is somewhat ugly formulae, which I'm not going to show you. So I'll just give you the one that gives the nicest picture, which is the spectral data, the branch points of the spectral curve. So remember that we ordered the branch points so that we ordered them from closest to the origin to furthest from the origin. And that after blowing up, we had a situation where the blown up branch points were all outside the unit circle. So, I mean, essentially in our blow up, in terms of the spectral parameter, we have taken the origin and we've blown up the entire origin to the unit disk. And everything that was outside the origin has gone to outside the unit disk. So it's everything. And the things which were already outside the unit disk, they've just disappeared. They've gone off to infinity. But of the things that were originally in the unit disk, what about them? Have they disappeared off to infinity, or are they somewhere in the finite plane? Because they're our only chance. So it's always good to have a picture. I'm sorry I don't have more of them, but at least looking at this one. So of the original branch points, the ones that were originally outside the unit circle, when you blow up, gone to infinity very fast. The others, after you blow, so you're blowing up by the size of this one. So that one's not heading off to infinity, but all the others that were bigger, that might blow up to something which is finite and out here, or it might blow up to infinity. And whether, like, how many of them go to infinity is actually giving you a lot of information about the geometry of the resulting minimal surface. So there will always be some number d tilde somewhere between 1 and g, because that's the number of branch points you had that were originally inside the unit circle, so that whenever you're bigger than that number, that your branch points did disappear to infinity, whilst the ones that are less than or equal to that stay in the finite plane. They're outside the unit disk, but they stay in the finite plane. And then the limiting spectral curve is just the curve that had the right form, so it's branched at 0, and it's also branched at those remaining points. So in particular, we're certainly not getting all minimal surfaces in this way, right? We've required that those branch points are all sitting outside of the unit circle. And the genus has dropped in general, right? Because you had all the branch points that were originally outside the unit circle, they've all gone. So even if you keep, even if your d tilde here is G, and you got to keep all the ones that were originally inside the unit circle, you have disappeared off at least half of them and maybe more. All right, so an example. I'm going to give a bunch of conditions that result in the minimal surface that we blow up to being the helicoid. Now for the helicoid, right, it's the only ruled minimal surface in R3, and it's fairly reasonable to write down all this data for it, to write down its potential, to write down its extended frame, to write down the conformal factor, to write down its spectral curve. And in terms of the blow up, here are conditions that mean that the original sequence of CMC torus immersions blow up to give you a helicoid. So first of all, you had to start out with something that had odd spectral genus. We need to be in the situation that we are actually doing this blow up. So no subsequence of the original sequence converges to a surface immersion. So we did need to blow up. And we are going to assume that that all of the, so we had one route that was closest to the origin. And if we assume that all the others go to zero at a slower rate than it does, then so that basically means that after we blow up, so they're going to zero slower. So they are staying once we divide by that blow up. Then it's telling us how many branch points we have left, right? And then we also have to assume that the smallest term in the spectral divisor goes to zero at the same rate as this point that was closest to the origin. And we need also a symmetry condition. So under those assumptions, then we can go through and check that the blow up of the sequence of CMC tori is actually a helicoid, which was a nice sanity check after this. So yeah, I mean, the two things I wanted to describe are that you can describe these immersions in many, many different ways. There's a plethora of equivalent information, but in particular in terms of a matrix polynomial that only depends upon the geometry of the immersion around some point. And then you can blow up around that point and get that your sequence of CMC immersions after the blow up converges to a minimal surface. All right, I'm done.
Thank you very much, Emma.
Thank you.
So if you were to rephrase this in terms of solutions of the sinh-Gordon equation and the Liouville equation.
Or KDV, actually. I mean, you can do Liouville if you want, but you can do KDV.
Oh yeah, well, I don't know.
That's nicer, right?
But so you're saying somehow you take a sequence of solutions of one equation and the limit goes to a different equation, or yeah. And what is the statement then in those terms?
So everywhere that I said CMC, replace sinh-Gordon, and everywhere that I said minimal, you can put either Liouville or KDV, depending which way you want to describe things.
I mean, I understand Liouville, but I'm surprised that KDV. Why?
Yeah, if you make the Hopf differential constant, which we have done, then you can describe these minimal immersions in terms of KDV. I mean, from my point of view, it's that the spectral data is KDV spectral data. So you can take that and invert that to a solution of KDV instead, if you want. But if you like, I mean, I didn't explain that at all. So And so if we want to be safe, let's stick with Learville, because that's something that is somewhat explained in the talk. So it says that after blowing up, and again, like your conformal factor, which was a solution to sinh-Gordon, right? So that's a function of your parameter z. So it's saying that after blowing up the parameter z and blowing up the function, so you do have to rescale the conformal factor as well, then a solution to sinh-Gordon in the limit becomes, so a sequence of solutions to sinh-Gordon after blowing up will give you a solution to Learville.
And you have to exclude that it doesn't just converge.
Because it doesn't converge to a solution of sinh-Gordon. Yeah. And you've got a couple of other kind of technical assumptions. But yeah, and I think part of that, I mean, I hit it all the way, but the difficult thing is knowing like how to blow up. And also then the question is, well, okay, you've blown it once and you got a solution to Learville. Can you blow up again and get a solution to something else? And it would be, I mean, I don't know of other work that does something like this. Maybe other people do, but it would be very nice to have some kind of more general understanding of what it is you need to do to go from one kind of system to another kind of system, like what the characteristic properties are that tell you this is what you're going to get in the limit.
Yeah, no, and it's very surprising, right? I mean, to end up in a different, completely different setting in a mind. Right?
Yeah, I'm not. I'd be really interested to know if people have seen something like this in a different kind of scenario, because integrable systems is such a broad field where it could easily be that there's some people out there for whom blowing up and changing the system that you're talking about has come up in a different context, but I've not seen it.
There's lots of blowing up everywhere, but I haven't seen it in this setting. Then let's thank Emma again. Thank you very much.
Thank you.